We were doing differential amplifier and we have already looked into the large signal analysis, and now today we shall see some of the active loads, different kinds of load which diffam can have, and how we calculate the difference gain and the common mode gain. Okay. So the first one which I am going to calculate is a normal active mode in which M3 M4 are in saturation by force that the gates of both are n channel, but as I said they can also be p channels. For this differential amplifier which I just showed with a active load, okay, the equivalent circuit you can start looking from that circuit again. If you have the figure, please keep this figure up so that you know what I am saying. I am referring to this figure, okay, and there are M1, M2 are the drivers in which inputs received, M3, M4 acts like loads, and M5 is the current source. Okay. Okay, so with this for this amplifier, and since we said the difference mode is always used that VGS1 is minus VGS2, which is equal to VID by 2 each of them, plus VID by 2 at Vn1 and minus VID2 at Vn2. So difference is VID by 2 minus of minus VID by 2 means VID. So essentially the difference can be divided half on the input 1 and minus half on the input 2, so that the difference signal remains VID. Okay. So if I do that from the gate side, if you see at the gate side, there is a VID by 2 signal which is going to be your VGS1. This is my source of the equivalent source for both M1 and M2. One can see from here the source, one can keep seeing here, this is our source, and down there is a transistor M5 which is your ISS current source, and it has a resistance of RO5, it has an output resistance of RO5. Now if this is your RO5 which is going to the ground, and each signal is also provided to the ground. Please remember signals are from VID by 2 to is taken positive and ground is the second terminal. So this is your second terminal. For VGS2 the signals are minus VID by 2, therefore it is same the opposite signal signs, plus minus, this is plus minus, this is plus minus, okay, and this source then is a common for both M1 and M2, and by simple thinking it is there at the drain side you have GM1 VGS1, GM2 VGS2 shunted by RO1 and RO2. Is that clear? This is same two circuits together I am putting in one way because source is common, so I am going together on the both circuits. Then for the VGS3 and VGS4, please remember this is something interesting. These transistors are connected at the outputs here VO1 and VO2. So this is your VO1 and this is your VO2. So a transistor in saturation will receive some signal. You can see from where, since there is a potential going to be here and this is going to be grounded. So there is a VGS available for both the signal as if is going for both M3 and M4. Is that point clear? If there is a potential here, they act like a VGS for M3 and M4. Okay. So those signals, if you look at it, can be represented as GM3 VGS3, GM4 VGS4 shunted by their resistance RO3, RO4. But the interesting part is this potential across, since please remember this gate is common to both and going to the ground, the potential here essentially is VGS3 and VO2 is VGS4. This is drains, these are drains of M3 and M4. Okay. Since this potential is VGS3 because you are connecting gate to the drain, okay. Okay, so this is again VGS3 which is also VO1. This is drain, this is drain. Since the potential across this gate and drains are common, the potential VO1 is same as potential VGS3, same way VGS3 is VO2. So what does that mean? This is equivalent of what? If the potential drop across a current source is the same potential, then what is the equivalence of that? There is a resistance there of what value? 1 upon Gm3 and 1 upon Gm4. Please remember, this is a simple circuit theory. If the potential is VGS3 and the current source is VGS and current source is Gm VGS, it has a resistance of 1 upon Gm, as straight as that. So if I use this equivalence, also I do some interesting things. You can see, since VGS2 and VGS1 are in opposite sense, okay, minus VGS2 is going to come. The current through RO5 is in opposite sense. If this goes like this, essentially the VGS2, because of minus, one current goes like this, the other current comes like this. Is that point clear? VGS2 is minus VGS1, yes. So this current is going through this in this direction, this is minus, so as if the current is coming out of this on the RO5, generally GMs are equal. VGS1s are smaller, okay, very small value. They may not be exactly same, but maybe because VGS1 is minus VGS2, these current sources are equal if GMs are equal. So what does mean, how much current is really flowing in RO5? 0. Is that point clear? If GMs are equal and VGS1 is minus VGS2, current through RO5 is 0, and this fact I will use everywhere now, okay. If this is grounded physically by us and no current flows through, what is the condition for the source? It is equally grounded. Please remember AC ground and don't connect it to DC ground. This is an equivalent of an AC ground. Assumption is GM1s are same as GM2 and other signals are opposite sense, then automatically we say there is hardly any current in RO5, and since there is hardly any current in RO5, this potential is same as this potential. Is that no current means the potential here and the potential here must be same, otherwise current will flow. Is that correct? If we say no current, the potential at the two ends of RO5 must be same, no current. Is that clear? This current goes through this direction in RO5, this is minus sign, so this current comes out of this, and if GMs are equal and VGS1 is VGS2 by magnitude, the two currents are cancelling in RO5. So there is no current in RO5, equivalently saying, of course GMs are different, they will flow, but otherwise, and even if they are different, they are very small, difference will come, okay. So practically what we say, drop across this is very small because very little current can flow or zero current can flow. So this potential must be same as this potential. This is what AC currents are, AC drops are. Minus VGS2. Is that clear? That's why it is minus. No? Is that condition is for difference mode signal amplifier, we are looking for VDDs. Is that clear? So essentially it's a difference mode amplifier, the currents will be in opposite sense. Is that correct? So if I use this theory which I did here, then I have a very simple circuit, which is what the circuit analysis people do. They just forget about RO5, put your source of this transistors as to the ground, okay. We have removed RO5 from here, equivalently saying this is ground, this is GMVRD by 2, GMVRD by 2, this is RO1, RO2, 1 upon GM3, 1 upon GM4, RO3 and RO4. Do you see two circuits? Actually they need not have been drawn one over the other. This is independent circuit and this is independent circuit, in between there is a ground. Just to save space, I showed you one ground, this one, the opposite one. Is that clear? These are two independent circuits. Is that correct? The VO1 and VO2 are independently seen by us. Is that correct? Since the source is common, I am using common line here, one on the this side and one on the other side. So this is drain, this is drain. Please remember these are drains of both the transistors. Outputs of M1 and M2, okay. Now if that is so, this is a parallel combination of RO1, 1 upon GM3, RO3. This is a parallel combination of RO2, parallel 1 upon GM4, parallel RO4. So same thing I just want to show. This two circuit can be as if independently shown to you, because this is source which is grounded. Drains of, yeah, essentially we are saying same. Okay. Essentially, so that is the source of N channel, but which is connected to the same terminal. Okay, and therefore we say they commonly call drain of M1 and M2. Okay, this is drain of M1 and this is drain of M2. But we have put the sign opposite now. Current source, ये इधर जा रहा है, ये इधर जा रहा है ना. Okay, okay, yeah, that's right. If it, then I will write minus. You are right. But here I did do that. Is that clear? I did this same thing here. Yeah, it is going to the drain. This is coming from drain to the ground. This opposite sign has been taken care. Okay, opposite sign. So if I have now these two circuits, what do I calculate? VO1 and VO2. How much is VO1? Quickly say me. Minus GM times this load, and this is plus GM times this load. This is plus, sign is this way. This is plus GM times this load is the output, minus GM times this load is the output, is VO1. Is that clear? So if I calculate both of these, which I did, you solve yourself again. This is only to show you how to solve circuits. So the gain of first, VID by 2 plus, is VO1 by VID, GM1 by so much. Similarly, so if I write this expression, solve, it is minus GM1 upon 2 plus GM3 plus GO1 plus GO3. Why I put G's? Because 1 upon R plus 1 upon R plus GM, you have to invert it again, so if expression becomes long enough, so many times add conductances if they are in parallel. Is that point clear? Whenever conductance, you have parallel things, you can convert them into their G's and add them out. Okay. Essentially when you want to know R, you will have to do 1 upon again. Okay. But this is much easier to do conductances. Okay. So AVD1, okay, oh sorry, by, oh no, 2 I have taken care through this, I think. Okay. Just keep whether it is. So similarly I can calculate AVD2, that is VO2, and I calculate. The trick about this game is, if GM3 is much smaller than GOs, will it be right to say so? Transconductance of an amplifier will be the order of 10 to power minus 2 or minus 3 amps per volt. Okay, whereas what will be the order of conductance is minus 6 or minus even higher. Okay, tens mega ohms or 1 mega ohm to tens of mega ohms. So when I shunt a smaller resistance by larger, larger can be neglected. So roughly one can say, that's why I say roughly, it is root GM3. If I substitute GM in this formula at ISS by 2, at ISS by 2, all that I am going to get is gain is W1 by W3. Is that correct? W1 by W3. Similarly I get this, yeah, 2 will come because this 2 is appearing here. Okay, I should have put 2 here, sorry. But that is same, that will anyway difference, it will get added. What you are saying is right. VID is VID by 2 minus of minus VID by 2. So if I calculate for this, they will sum in the difference. So VID will anyway come when I actually add the two gains. 2 by 2. But same for the other one also. So by when I take the sum of this, VID by 2 minus VID by 2 will be get subtracted out anyway to get you VID. Is that correct? So if I get AVD, what is the, when I sum this 2, I get VID, AVD is W1 by W3. What does that mean? What is the advantage or disadvantage I see in this expression? The difference gain does not have any quantity which is dependent on what? Only the size of the transistor, but nothing else. No VT, no beta and dash. It is independent of transistor parameter except size, is that correct? It is independent of everything else now, not even ISS, okay, not even ISS. So essentially this means that I can fix the difference gain by what should I do in this figure? I should adjust the size of M1, M2 with reference to M3, M4. The ratio of these, why I am stating I did not take lengths, because lengths in all transistors will be identical unless said otherwise. Lengths of all transistors will be the smallest channel length available to you. Is that correct? All integrated circuits in analog uses common channel lengths for all the transistors, so is in digital. Channel lengths are never changed, okay. Because if you increase channel length, what will happen in digital or even here? The time taken for an electron to go from source to drain will increase or decrease? Increase, because the channel length is higher. So what does it mean in time term or frequency term? It will slow down the circuit. So at no time the channel lengths will be actually increased. However, if you recollect back, I say lambda is somewhere related to this, and if I want lambda to be small, what do I gain if lambda is smaller? R zeros are higher. So what I am now trying to tell you, they used longer channel lengths, okay, if you want output resistance to be higher. But if you want larger gains, you better use larger widths. Is that issue coming to somewhere? GM R0 term is now hitting opposite way. Increase GM, increase size, increase R0, decrease, increase lengths, okay. This means there is some optimum will appear. Is that word clear to you? GM will go proportional to root W, R0 will go 1 upon L, okay. Now essentially if I increase W, yeah, GM will increase, okay, or W by L, essentially if I increase, I will increase GM. But if I increase lengths, I will improve R0, okay. GM R0 is essentially somewhere intrinsic gains. So इसका क्या मतलब है, एक बढ़ाओगे तो दूसरा डाउन होगा, तो there is some maximum minimum will occur, okay. U-turn, थोड़ा बढ़ेगा फिर नीचे आ जाएगा. So can't have longer length, can't have much smaller lengths. You will have to adjust many times. So the idea is in digital circuit, so is in analog, don't change lengths often. Use common lengths for everyone. And what is the available length of device? The channel length given by technology people. Let's say it is 0.25 micron process, the channel length is 0.25 micron. So use everywhere same lengths. Is that clear? This is a sacrosanct number, channel length, use everywhere else, same else. So when I divide W by L by W1 by L1 upon W2 by L2, L1, L2 are same, so it is only ratio of sizes, okay. But remember it is W by L ratio I am taking, lengths being same I am cancelling lengths. Essentially it is the size ratio W by L of the one by W by L of the other. Is that correct? But lengths being same, we only say width ratio. Is that clear? This fact is understood by all analog designers or digital designer when they go on the chip, because that's the way everything should be uniformly kept. On a board you cannot do anything like this. Why? The circuit devices will be given by someone else, they may have anything we don't know, so we just go by and connect and hope for the best. So no integrated circuit equivalence can be created by breadboards. Is that point clear to you? Because discrete devices are never identical. Is that clear to you? Discrete devices are never identical. So what is the experiment I suggested you in the lab to do that? They look like IC. There is an array of transistors you use, in which transistors are most likely to be identical, and then you can make a diffam through that array. Is that correct? Otherwise no way you can actually create an equivalent circuit, equivalent IC in a discretes, okay. So what is that trick I am trying to say? So don't make a op-amp out of discrete components, it will never give a good gains or good bandwidths, okay. However, which amplifiers can be used with single discrete transistors? This normal amplifier, common source, common whatever transistors you have, you can always use them as a normal gain stage wherever you need. But if you want a diffam or you want to have an op-amp, at no time try components discretely and connect, okay. However, as I said you, yeah, and if you pick up array of chip which has a more transistors, you can pick up inside that, there will be pins which will be available for each source, drain, gate for each of them, okay. If there are array of 4, there will be 12 pins, plus VDD pins plus many other pins. So if you use that, then you can make a op amp. So try it if you can get in our lab, but that's okay. At least you have seen that commonality of transistor parameters are guaranteed to some extent if it is on an array. Otherwise, take one transistor discrete, put here on the breadboard, this will never have any gains available. Is that because of the mismatches it will have? Okay. So this fact has to be understood, that why I keep lengths constants everywhere, because all ICs will have common lengths. Okay. We never change that, unless of course, as I say, I am looking for a buffer stage in which I want really R0 to be of particular value, then I may tailor it for that specific particular device. Okay, that is called tailoring, and that time this is difficult to tailor because it is an extra mask, as we say, and if you do extra masking, that means, please remember in circuit, I do not know, you have not been told any technology, we go through around 20 odd mask steps, as we call patterning. Okay. Each mask patterning step cost you around $1 million plus. Okay. So if you add one mask additionally for doing one separate process for one transistor, then you are almost asking me to do additional money on the same chip, $1 million. Okay. Of course, number of chips will come out of the wafer, but it will cost very increase per mask, and therefore in integrated circuit you are avoiding extra mask. Okay. But if you need it, yeah, it's possible. Okay. Okay. So having shown you the gains, the output resistance, how much is the output resistance of a diff amp? How much is RO1? The GM3 plus GO1 plus please remember, how do I look at RO1? At this end, how many resistances I will see? RO of this plus 1 upon GM of this. Okay. 3 resistances in parallel or 3 conductances in series, GM3 plus GO1 plus GO3, which is roughly equal to GM1 upon GM3. By same argument, RO2 is 1 upon GM4, GO2 plus GO4, which is GM4, and the ROD is essentially called sum of the RO1 plus RO2, which is nothing but 2 by GM3 if 3 and 4 are identical. Oh, please remember now, in this transistor the connection was of this kind. This is diode connected, this is not diode connected. The GMs occur only when VGS and VO is same across, that means drain is connected to the gate. Is that correct? Only then the potential is same. This potential is same as this potential. Is that clear? Only then that condition is satisfying, that the drop across a GM current source has the same voltage drop. Then only it becomes GM. This is called diode connection. Only in diode connection the actual output resistance is 1 upon GM. Shunting R is fine, but that R0s are so high, so it is only 1 upon GM. But in a normal this VGS and VDS are not same, na? So they are giving you a R0 only, there is no 1 upon GM term because the VDS is not same as VGS. Is that point clear to you? So this issue has to be understood, that is why this was called active source, active current loads, active loads for N channel transistors. Okay, is that clear? So only what time you should use GMs? When there is a diode connection. Okay, otherwise no. Okay, otherwise it's a normal transistor with R0 sitting, its VDS is not same as VGS. Is that correct? Same potential drop है तो ही GM, you understand ना? Current, ये ध्यान रखो हमेशा, ये word कभी मत भूलना. If this is GM some V and this is V, this is equivalent of a V, and then this is 1 upon G. You can see now V by 1 upon GM is the current, which is GMV. Is that correct? So these are only equal when this condition is met, otherwise it is not equal. So whenever that is the circuit I showed you, I connected them and therefore this GM term appeared. Now we will do in which case this does not occur, and in that case we will remove that GM, it will be only ROs. Is that correct? Why I am showing you parallel? Because I want to tell you ROs may come or GM may come depending on whichever is smaller among them. Okay, that may dominate. Whichever is higher than them, that may dominate. Is that okay? ROD is between the two terminals of VO1 and VO2. एक का resistance इतना और एक का resistance इतना है, तो net terminal to the ground is equivalent of 2 times that. Okay, so the next, which is most important, okay, this is the most important circuit which all chips will be using. Okay, what is the difference between the last one and this? What kind of load I am using? No, P even there I could have used, but what is the kind of load I have used now? It's called current mirrors. The gate of this is connected to the drains of this. Is that correct? This is called current mirror. So whatever current is here depends on the size being equal will be passed on into current in M3 should be equal to current in M4 provided size of M3 is same as size of M4. Otherwise how much? If this is double the size, twice the current will flow. Okay. Now this current mirrors, which is what I have shown you sideways. This is a standard current mirror which is equivalently put there. Now this is the standard, as I say, first stage of an op-amp. This is the first stage of an op-amp. Is that correct? This is the first stage of an op-amp which is going to be used. The next stage is what we call single-ended amplifier, and that will become two-stage op-amps. Okay, this you may call one first stage op-amp. Okay, then we will have a two-stage op-amp, and we may finally have how many? Three-stage op-amp. What is third stage will be? The buffer. Do you understand the difference between buffer and a common normal gain stage? The buffer normally provides you currents. What does it do? Larger currents. Is that correct? So एक buffer का characteristics हमेशा ध्यान रखो. This is like equivalently saying like this. It will either provide current from here, from power supply to the load, let us say it is a capacity load, or it will discharge this capacitor to the ground through the lower one. So what does that mean? At a given time, either it will source or it will sink. Is that correct? So that is called the buffer stage. Is that buffer is word clear? The output buffers are always designed for in which either it will source the current or it will sink the current. Is that correct? This is the third stage of an op-amp, which is the buffer stage. Okay, but let op-amp come and we will come to it again. Okay. So this is the first stage which we are looking into. Now here is something which the real circuit may look like. This is your current mirror. So the current ISS is created from where now? Please remember what is the difference between last stage and there I applied some potential VGG here to get that current source. Is that clear? In the last case I applied to R5, M5 a supply voltage and I got the current source out of it. Now I say why do that? I may as well use a current source, okay, current mirror. So here is my current which I am creating, which I am now transferring to M5, okay. Keeping what now what I can do tricks, I can use different size here and different size here and I can adjust this value by the ratio of these two, okay. This we are already done, okay. This is your current reference VDD by, since these are equal, VDS and VGS are equal, we just calculate and find how much is current here. If we know this, please remember in this case again VGS 6 and VGS 5 are same, therefore the currents in M6 and M5 are same with the size ratios. Is that clear? This is this we did in mirrors. Okay. So this is a biasing circuit. What is this called? This called the biasing circuit. Can I replace R also? By a transistor shunting to the drain, I can convert this as a R equivalent of that also. So I can replace R also by a transistor. Right now I showed you a resistor, but in reality I may have a transistor there, okay. So I may have a current here which I can fix and I can then mirror it into this whichever value I am looking for. One method is actually create same current, transfer here as 1:1, or make any current here, take a ratio of these two and push the current of your choice in M5, okay. I want say 5 milliamp current, I may create one here but keep a ratio of 5 and pass 5 milliamps here. Is that clear? So that is the way we can create the current sources at M5. This is a potential Vp this is my M1, M2 and V this. Now few things you should know from here. Vn1 minus Vn2 is Vid, which is nothing but Vgs1 minus Vgs2. We as usual apply Vid by 2 here minus Vid by 2 to the other gate. We also know Vgs1 is equal to Vp. What is, why I am saying it? Vgs1 is the same as Vg. I just now said the resistance of RO5 is large enough, then, and if the two currents go opposite, this potential can be treated equal to VSS, and right now for DC it is minus VSS, for AC it is how much? Ground. So we say Vp is close to the ground, is that correct? Because I am not sure whether they are exactly identical, so I may say okay, Vp is roughly close to the ground or can be treated ground. So Vg or Vgs is same. Vg and Vgs, because S is going to the ground, so Vg or Vgs is same. So we say Vgs1 is Vg1, Vgs2 is Vg2, condition again same as just now I said. Is that point clear? Just now I solved the case, I say Vp can be treated equal to close to the ground, okay. If that is the equivalence we agree, then we calculate, this circuit should be kept sideways, this I am keep using. There is a potential node which is essentially VO1, which I am calling as Vx for the simplicity, okay. Is that correct? Why I am not calling it VO1 specifically? Because I am not picking an output there, okay. I am only picking an output at this end, so I call that node as Vx, okay. Is that point clear? This is essentially VO1, but this I am calling it, because VO1 means either I am taking an output. I am not calling this node VO1 essentially because this VO1 means I am picking an output, which I am not. I am only keep finding what is the value of voltage here, okay. Please remember, by making this connection, this is my gate, this is my source. Can you tell me why source are upwards in P channels? Poles must go down, okay, otherwise there will not be possible of same direction currents, okay. So you can see if I connect it like this potential which is here, this is shorted, this potential and this potential are same, is that correct? This potential are same, this is what I used. No, because with this value itself I have calculated the current, you understood? Here I am not treating ground, here I am treating minus VSS as the value and VDD is this value, so when I calculate reference current I am using VSS there. So when I am keeping this, by making of choice of this which is the gate of this, I am ensuring this VGS is positive enough greater than VT with VSS. That is what I did now. When I calculate the current and I assume this transistor in saturation, I am actually forcing the value of resistance such that transistor remains in saturation with that kind of VSS available. If it is ground, this value will change, is that correct? If minus VS, it will change differently, okay, but it will force you both transistors to be in saturation. So what is VGS4 in your circuit? Keep watching that. How much is VGS4? The VS4, which is the source terminal of both the transistor, minus Vx, ये source है, VS4 and VS3 are same. This potential minus Vx is the VGS, is that correct? We know this is grounded for AC, but right now as I said, this is Vs, potential of this, minus Vx is the VGS, source. So this is, or rather Vx minus this equivalently saying, okay. Vx minus Vs is VGS, yeah, that is what I wrote. No, that is because it is a P channel device, it is a minus potential will appear, okay, okay. So we say VGS4 is VS4 minus Vx, okay, you can also call it minus, fair enough, okay. This is VS3 minus Vx Please remember Vx is the output of first M1 M2 amplifier with M1 receiving VID by 2. Please check it what I say. VO1 is the output of a diffamp at terminal Vx when M1 receives VID by 2, M2 receives minus VID by 2. Is that correct? So we know Vx is nothing but GM1 VID by 2, RO1 parallel RO3, and for your case someone was asking now put 1 upon GM3 here also. Is that correct? If that's so, this is RO13 GM is sum of this. So Vx is VO1 minus GM1 VID by 2 into this. Since RO13 is normally equal to 1 upon GM3, so Vx is minus GM1 by GM3 times VID by 2. For one input from the M1 side, the output is Vx is minus G, we did it for common this amplifier earlier, we are just writing the same expressions. So it is GM1 by GM3 into VID by 2 is the Vx, okay. If that is so, can I calculate VGS4 therefore? Okay, so having done this, I calculate VGS4 which is GM VID by this. Now I have for these this M2 M4 amplifier, you look at this I am talking. The VO is decided by how many inputs? ये भी ऐसी है यहाँ पर, ये भी ऐसी है यहाँ पर. M4 is also an input, has an input, and M2 also has an input. So the output voltage by superposition will say is the available because of this plus available because of this. Please remember there is a signal coming at the input of M4. VGS4 is a small signal which is coming as an input there. There is an input anyway here. Is that correct? So this potential is not only governed by M4 inputs but also by, or sorry, not only governed by M2 inputs but also by M4 inputs. Is that clear to you? Since this value in this case is signal available to you, small VGS4 or VGS3 is available to you, this acts like an input to M4. So it will also amplify. This is a given input anyway by us, so it will also amplify. Is that correct? The sum total will be the net VO value for you occurring because of M2 and M4 पे भी इनपुट है और M2 में पे भी AC इनपुट्स है, दोनों मिलके आउटपुट देंगे अब. और the only thing is, since transistors are assumed in saturation, we say where signals are small enough, then what is the condition I am satisfying? Linearity. Superposition theorem is only valid if it is in linearity. So our assumption is because of the condition I enforced, both systems are in linear mode. Therefore superposition is possible. Please, is that point clear to you? Superposition is only and only valid if system is linear. And please take it, I repeatedly tell you, which is the question I have been asking in here. Y is equal to mx plus 3 is a line, so like looks like linear but the system is non-linear. Okay, this fact has to be appreciated in whole of the life of electrical engineers. Okay, this is a AC signal which is connected here. Output of M1 coming at here is connected direct to the gate of M4. Is that correct? वो करंट मिरर किया ना आपने, तो कनेक्ट कर दिया, तो वहां जो यहाँ पर जो आउटपुट है वो इसका इनपुट हो गया, इसके कारण ही तो इसका गेन बढ़ रहा है बाबा. इज दैट करेक्ट? इस दो तरह से मैं आउटपुट पे ले जा रहा हूँ आपको, एक यहाँ से ला रहा हूँ और एक यहाँ से ला रहा हूँ. यही इसका ट्रिक है और यही इसका स्ट्रेंथ है. Okay, so all that I did, I solved these problems. I calculate VO due to VGS4, VO due to minus VID by 2. I also assume all transistors like GM1 is equal to GM2, that is M1, M2 are identical and M3, M4s are also identical. but M1, M3 and M2, M4 are not identical, only pairs are identical, M1, M2 identical, M3, M4 identical, GM3 is GM4, RO3 is RO4. I solve this problem, that you only see this is the line I said, VO VGS4 VO VI minus ये दो सिग्नल का सम करना है आउटपुट पर, is that clear? The next is this. So VO, this is due to VGS4. Do you know why this is VGS4? इसको VGS4 को VID के टर्म में जो एक्सप्रेशन निकाला वो मैंने इसमें सब्स्टिट्यूट कर दिया. Okay. This is due to VID by 2 into ये RO24 क्या है? What is the output resistance at V0? The output resistance of 2 M2 parallel to the output resistance of 4, and there is no GM terms appearing here because it is not diode connected. Whenever diode connection, make it GMs 1 upon GM. If no diode connection, it is only RO. Is that correct? So if that is as I say, ROs will get cancelled simply because not necessarily removed. If that numbers are, let's say RO is not very high, in which case parallel combination must be taken care. But as I told you, GMs will be order of -2, -3 amp per volt, okay, where ROs will be order of -6, -7 per ohm per current per this. So essentially we are saying that ROs are much larger than 1 upon GMs, okay, and therefore 1 upon GM is a good approximation in most cases. But I have never written directly, I first show you parallel combination and then I say if this is larger I can use that term. So in real life, calculation wise never leave terms, numerically they will get eliminated. 1 upon 1000 plus 1 upon 5, do whatever you, it is a 0.2 only, okay. So that number will automatically get eliminated, you need not do anything. You solve parallel combinations, the other terms will be small enough to be used in the expressions, is that. But if you are sure and you can write, there is nothing wrong, these are too high compared to, I use this. That's what electrical engineers are all about, okay. Okay, what is the output resistance of this stage? So AVDD is VO by VID, GM1 upon GO2 plus, इसको सबको सॉर्ट करोगे तो ये आ जाएगा. ये बड़ा एक्सप्रेशन देखो क्या दिखा रहा है ये. What is the upper terms are talking about? What is this upper term is because of GM1 of M1 which is same as GM2, is that correct? GM1 is decided by what factors? Please look at it, what factors GM1 is decided? Beta dash, which is a given technology, the size ratio W by L into the bias current ISS. Where from this is fixed? From the mirror side, which I am fixing. What is GO2 GO4 is lambda 2 plus lambda 4 into ISS by 2. I can take ISS above now, okay, and I do. So one thing very interesting is happening and that is why I have shown you this expression. I will come back to it, this expression, please note down, this is relevant expression in our difference gain value. Beta n dash W by L 1 divided by ISS upon lambda 2 plus lambda 4, they are equal than 2 lambda, okay, then this 2 will also go. Oh, I just now showed you and okay. The output resistance seen at this terminal is because of this, and this is RO2 and this is RO4. So इस terminal पर दो resistance parallel में है ना, so RO24 is a parallel combination of RO2 and RO4. Did you see GM term there? No, why? Because it is not diode connection, it is an open-ended blocks, okay. So I calculate this term, I calculate the output resistance R0 which is RO2 parallel RO4, then I see very interesting two functions. The difference gain is proportional to W by L of M1 or M2, they are equal, okay. M1 ट्रांजिस्टर इज आइडेंटिकल टू M2, डिफैम के जो ड्राइवर्स हैं उसका साइज सेम होगा, तो उनका साइज क्या होगा, लार्जर द W by L, लार्जर इज द गेन, is that correct? Larger is the size, larger is the gain. But one interesting feature I am seeing, this difference gain is inversely proportional to root of ISS. What is it trying to say? That is, if you work at smaller currents, your gains are higher, which is very typical. Na? Normally what do we say? Pump the power and get the gain. It is now trying to tell me that reduce the bias currents. Okay, if you reduce the bias currents, differential gain is higher. Okay. However, and they are also inversely proportional to values of 1 upon lambdas of M2 and M4. If you see your R0, which is 1 upon lambda 2 by lambda 4 this, so if you see RO24 value, it is 1 upon GO2 plus GO4, which is 1 upon lambda 2 plus lambda 4 into ISS. So the output resistance is inversely proportional to ISS. So if you reduce ISS, output resistance increases. If you reduce ISS, your gain increases. So why not always keep small currents? Power dissipation is lower. इसलिए मैंने बताया कि when I go for op-amp, this is the place where I will come back to. So no, if I reduce ISS, I may lose something. This condition is valid. What I have shown you is a valid statement. There is nothing great thing going wrong. Okay. Is that correct? Then why are people do not want much smaller currents? The net output resistance of diffam, do you want higher or lower? I have not stated so far. Is that correct? डिफैम का आरओ कितना होना चाहिए ये नेक्स्ट स्टेज बताने वाला है आपको, और यही इसका फैलेसी है कि यू कैन नॉट डिसाइड आर्बिट्ररी लाइक दिस बिकॉज यू डोंट नो व्हाट लोड यू आर कनेक्टिंग. इज दैट करेक्ट? That is why too much smaller currents or too higher currents both may actually hurt you very strongly. Is that clear? Okay. Now, but this is not the only reason. There is a major reason which we will see later. अभी एक मैंने परसों के दिन फिगर निकाला था आपके लिए ओपैम्प का. ओपैम्प का जो आउटपुट रहता है वो एक कैपेसिटिव लोड पे ड्राइव करता रहता है. इस कैपेसिटर को चार्ज करने का करंट कितना होगा? CL dV0 by dt, and this should be supplied by the buffer currents either source or sink. और ये सोर्स सिंक करंट कहाँ से आ रहे हैं? ये वो ISS के से ही मिरर होके आ रहे हैं. सो इसका मतलब यदि ये ISS से रिलेटेड हैं, so what does this essentially will tell? If ISS is smaller, the time taken to charge or discharge this capacitor will be larger or smaller? Longer time. Smaller current will charge or discharge the capacitor slower. Is that correct? This term dV0 by dt is called slew rate. dV's output charging to high or low is called dV0 by dt is called slew rate, and that is decided by ISS by CL. So if you want larger slew rates, which you will require for high speed performance in connections, then you must have larger currents. But if you have a larger current, your diffam stage will have lower gains. Is that correct? So ये चीज जो मैंने अभी तक नहीं बताया ओपैम्प की कि जो लास्ट स्टेज कनेक्ट होना है, that may finally tell me how much ISS I will be allowed, because someone will specify you. Is that point clear? What is one specification op-amp gives? Slew rate. It has 5 volt per microsecond. That's the slew rate they will say. Okay. Now to meet this slew rate for the given load, I know how much ISS I will require, and that's the ISL I will have to use back so that I can use a good defense. So ISS is not very much in my hand, which I showed you, as if I can vary ISS, adjust powers. ऐसा नहीं है, एक को हाथ करेंगे दूसरा निकल जाएगा, दूसरों का ये निकल जाएगा. तो ओपैम्प डिजाइन करते समय 100 चीजों का ध्यान रखना है. तीसरी एक और टर्म है उसमें जो मैंने नहीं बोली, ICMR, input common mode range, and output common output swings also are functions of ISS. Is that correct? So for a given op amp, how much is the output swing possible, how much is the ICMR given to you, what is the slew rate you are looking for, that all together will decide, and power dissipation will decide how much is your ISS and therefore how much is the gain. Is that correct? So it is not independent of everything. If I say I want larger gain, slew rate maar denga, or I should have very low loads, but if you have very low loads, then it's who are you to decide outside? Okay. So essentially design of an op amp does not just say ISS kam kar do ya zyada kar do, nahi, 4-5 parameters you have to keep adjusting so that roughly you get where you are expected to reach in the parameters. This is what the design is all. So is that clear why I am teaching you something more on the design side? Because at the end of the day, we are not going to use analysis everywhere. We are going to design chips or design component, design parts. So as a designer, I must know where I am constrained. Okay. And analysis, what does it give? It gives me constraint. Idhar kya hoga, udhar kya hoga, udhar kya. Then I know I know analysis. I know this changes this changes this. So if you want this, please give me this. Okay. If you want this, please give me here. Okay. So this is what designers do. Okay. So at the end of your course, if you learn this, that electrical engineers are not going to be just using the component, they are the ones who are going to design systems. Okay. As a designers, we must know my constraints, and if those constraints have to be met, analytically I must know what changes what. Okay. The whole course is therefore slightly changed from last so many years, is more towards design values, because second year se aapke dimag mein we want to push you that you are going to be designers in life. Okay. Even in banks, you will be making some portfolios or you will design something. Okay. So at the end of the day, engineers design something. Okay. Okay. It does. There is a limit coming. Maximum minimum is also fixed, but within that range also how much? Lower side or higher side? Your viewpoint is correct. If too much or too less, I may get out of saturation or go to cutoff. But assuming there is a sufficient range in which I will still remain in saturation. So usme bhi lower lu, to I am seeing something. Usme higher lu, to I see something. Okay. So during designs, this condition which you said is always true. Saturation to kisi halat mein hona hi. Everything else is after. If device comes out of saturation, you are in a non-linear zones. Okay. So we are not going there. Is that correct? So this point is well taken. But there is a still values, lower side and upper side, where to work. Okay. As an analysis, I don't care ना, जो value मैंने दिया निकाला वो output कुछ तो value आ ही जाएगा. 8 वोल्ट बाय एक एम्प आ गया तो भी मैं गेन कह रहा हूँ, ठीक है यार 8 वोल्ट बाय वोल्ट आ गया, ठीक है 8 ही गेन है, बट 8 गेन का एम्पलीफायर करके क्या करूँगा मैं 10 या 8 का. सो आई हैव टू नो आई मस्ट हैव 10 to the power 3 or 1000 or 500 गेन चाहिए मुझे. सो ऑल दीज वैल्यूज analytically I damn care what value I substitute in formula and whatever I say this is the raw. आपने गलत डेटा दिया, ठीक है, but in design I will be given specs, this is what I have to meet. So I am trying to give you some ideas how do I think. I means I don't mean a designer thinks. He knows analysis 100%, therefore we teach you analysis. From there I know each how it connects. And then given me final this, इस डब्बे में ही रहना है, तो क्या करना है, then I adjust, okay इसको ट्विक करता हूँ तो ये जाता है, अच्छा इसको थोड़ा करता हूँ, ऐसा कर करके we adjust the parameters. Is that clear? So this is a issue which I thought I must hammer on you. Okay, so please remember designs are part and parcels of all electrical engineering, for that matter engineering, but more so for electrical. Okay, so this finishes the amplifier part. Which amplifier we did? This is a diff amp with what kind of loads? Current mirror loads. The first case we did active load with diode connection, but there is a third one also, current sources itself. That circuit I will not solve, you solve. Which ones? The first circuit which I showed you first time, अच्छा इसमें यदि ये करंट सोर्सेस है M3 M4 तो इनके रेजिस्टेंसेस कितने होंगे, कितना होगा, इसमें GM आएगा कि नहीं आएगा, नहीं आएगा। इस ये इक्विवेलेंट R है, ये इक्विवेलेंट R है, easiest way to solve is this circuit, is that correct? This is RO3, this is RO4. So it is very easy to solve a current source load. Is that point clear? If this is simple resistors, then we already solved the diffam case with simple 2 resistors. So this is the case. Only advantage is this will have very large resistance. It's a good current source, means output resistance is how much for that? So RO must be very high, 10 to the power 6 or 7 for that. Because there is no GM term will appear here because VGS is not same as VDS. There is no diode connection going on. That means the voltage drop is not same across the current source as the GM times that. Okay. If they are same, then it is equivalent of a resistor. But otherwise RO is always there of the transistor. एक कर रहे हैं तो RO तो है ही आपके पास. So this is equivalent of a RO here and equivalent of a RO here. Okay. Just solve it. Okay. And you will get the gains for this also. Okay. So this finishes diffam as such. Before we quit, I will not solve fully but just show you how quickly we solve this. We have been telling as if the MOS diffams are only going to be used, but in real life which op amps are still on bipolar? 741. Okay. नहीं 741C भी है मार्केट में और आजकल C भी हटा के वो 741 ही बेच रहे हैं. So there are MOS op amps 741. Again, is 741 bipolar op amp will be better than MOS op amp or not? Is bipolar systems for an amplifier are superior to MOS systems or not? Okay, basic idea is GM. Is GM is better in bipolar for everything similar compared to MOS? Yes. So bipolar amplifiers will be superior to MOS amplifier any day in fact. But what is the cost I will pay for? Power. क्यों IC by KT कर रहे थे तो IC बढ़ा ही रहे थे आप. GM बढ़ा रहे थे ना तो वह एक्चुअली आपने IC बढ़ा के आया बिकॉज बीटा 100 से ज़्यादा है. IB माइक्रो में रखेंगे तो भी मिली एम्प से ज़्यादा IC लेके जा रहे हैं. Okay. Which means at the cost of power bipolar, then we say why not use the same technique in a MOS and use large powers. What is the problem? Because independently if I am using I may do that, but the power supply limitation may be increasing beyond 1.5, it may go to 5 volt, 10 volt, which no MOS transistor gates can sustain. What is the problem? If the gate gets larger voltage, breakdown. If the electric field is larger than the critical field, the MOS oxide may break down. So I cannot just arbitrarily increase VDD, is that correct? So we will have to work at smaller voltages, and for those the currents will be smaller and therefore GMs will be always smaller than bipolars for similar things. Only thing advantage I will get is low power. Since the chips are going to have low power dissipations, we will prefer MOS circuits on any silicon chips. Okay. Is that point clear? Why silicon chips are always presently MOS? Simply because of power requirements. Otherwise, you give me huge heat sinks, big silicon area, I may use bipolar circuit as much and do better performance. Okay. इसमें उसमें क्या फर्क नजर आ रहा है आपको? इसमें एक है कि उसमें VGS था, इसमें क्या होगा? IB होगा. Is that correct? उसमें VGS था, ये करंट ड्रिवन सर्किट्स है, वो वोल्टेज ड्रिवन सर्किट्स है. तो इसमें सब जगह करंट्स यूज करेंगे आप. IB1, IB2. However, actual inputs will be voltages V in1 and V in2. Okay. Difference is still VID by 2. Okay. VID point minus same method करेंगे. यहाँ भी करंट सोर्स है IE, उसके अक्रॉस एक रेजिस्टेंस है REE, ये एमीटर है. इसमें हमने जो इक्विवेलेंट सर्किट हम बनाएंगे उसमें एक RE रेजिस्टेंस बोला था हमने, RE स्मॉल RE या RS जिसे कहते हैं, emitter to substrate. That is normally used in many books, but that is around less than 10 ohms or 5 ohms, okay, in actual calculations. So if you don't use that, it's much easier to solve. Otherwise RS plus बार बार ये आएगा और ये 10 ओम और 1 मेगा ओम ऐसा बार बार रखते जाना पड़ेगा, इसलिए मैं बता रहा हूँ कि मेरे सर्किट में मैं उसको यूज नहीं करता, बट आप बुक्स देखेंगे सो यू विल फाइंड they will use this term because they are actually solving full circuit, so they will show you the RS part, small resistance which I showed you between substrate and emitter will be shown to you there. So circuit will have this resistance here plus this resistance here. So the emitter will see small resistance due to the emitter substrate this plus RE. मेरे इसमें मैंने वो resistance, which resistance I normally neglect in analog, RC, RB, RB dash and RS or RE. They may be used in case you want accurate analysis. In analytical में मैं सोचता हूँ बहुत minor रहते हैं, जब आप स्पाइस पे सॉल्व करेंगे तो वो ऑटोमेटिकली बिल्ट इन आएंगे, so you don't have to think, they will come there in model, okay, so they will take care of themselves, okay, you don't have to worry on that. Since you are doing numerically, आपने को तो अंदर क्या हो रहा है पता नहीं ना, हमको ये पता है कि I is GV. We are all the time solving a current matrix for a given voltage matrix with given conductance matrix. नोट्स के ऊपर हम ये कैलकुलेट कर रहे हैं, तो हमको कुछ भी मॉडल दे वो अंदर से लेता है, लो ना, हमको क्या तकलीफ है, हम तो सिर्फ देख रहे हैं कि कब आउटपुट आता है. That's what SPICE is of. You must have seen. You just give an input file and hope for the best. It may not be the best, unfortunately. That is where the problem is. Okay. See you then.